Picture this. You're standing on a multi-million-dollar trading floor.
Oh man, the energy in those rooms is just electric.
Right. It's insane. Millions of dollars are moving every single second, right? High-frequency algorithms are firing. Screens are flashing green and red.
Utter chaos, but controlled chaos.
Exactly. Or, imagine a totally different scenario. Say you're in the central command center of a massive metropolitan hospital network.
Oh, that's a whole different kind of pressure.
Yeah, you've got critical care data, patient vitals, real-time MRI scans flowing seamlessly to the surgical suites that need them right now.
Life or death data, literally.
Right, and then just bam. Without a single warning, the entire system just grinds to a halt. Everything freezes.
Every IT manager's worst nightmare.
The screens stall out. The data just stops. Thousands of dollars are evaporating every single minute on that trading floor. And patient care is suddenly, fundamentally compromised in the hospital.
And people immediately start panicking about hackers.
Right. But here is the wildest part. The culprit isn't some sophisticated nation-state cyber attack. It isn't a hacker breaching your firewalls or deploying ransomware.
It's a vulnerability hidden right inside the physical infrastructure itself.
It's wild.
It really is. It's what network engineers call a broadcast storm, or, an overwhelming cascading failure of network collisions happening at the very physical level of the wires hidden right there inside the drywall.
Which is just mind-blowing.
It is the shocking vulnerability of modern enterprise business. The reality that the invisible ones and zeros carrying a company's absolute lifeblood can literally just crash into each other on a copper wire, destroy the data, cripple the infrastructure, and bring a global enterprise to its knees.
That is the absolute nightmare scenario. And before we pull back the curtain on how to actually prevent those catastrophic infrastructure failures, let me just remind you that if you want to always maintain a competitive edge in this hyper-connected marketplace, take a moment right now to like, subscribe, and share this deep dive with your leadership team.
Yeah, you definitely want to keep them in the loop on this stuff.
For sure. Also, definitely check the description below. We've linked to a really substantial vault of corporate resources, structured wiring diagrams, and some technical reading that will help you actually visualize the architecture we're analyzing today.
Visuals help so much with this specific topic. But anyway, we are officially entering Chapter 4 of our 15-part Telecommunications for Managers series.
We're moving right along.
We really are. And just to set the strategic context here, back in Chapter 3, we mapped out the massive historical and architectural shift from those legacy circuit-switched networks where, dedicated physical paths were required for every single communication to modern packet-switched IP communication.
Right. We established how data is basically broken down, routed independently across these complex networks, and then reassembled at the destination.
Exactly. Which brings us directly to the focus of today's analysis.
Yes. Chapter 4, the physical and data link layers. Because to understand how a packet switch network actually survives the sheer volume of modern corporate data, and to prevent the kind of apocalyptic network crashes we just talked about, we have to look at the absolute foundation of your infrastructure.
You can't ignore the physical reality.
Right. This is where high-level digital strategy collides with raw, immutable physics.
And that collision between digital abstraction and physical reality is precisely where IT managers either succeed or fail. I mean, we are analyzing the very bottom of the OSI model today, the Open Systems Interconnection Reference Model, Layer 1 and Layer 2.
The basement, basically.
Exactly. Because a corporate manager might spend the vast majority of their day strategizing over, SaaS deployments, application development, multi-cloud architecture. But none of those higher-level initiatives can function if the physical foundation of the network is bottlenecked.
Or inherently flawed from the start.
Right. So let's start at Layer 1, the physical layer.
Which is funny, because when a manager hears physical layer, they immediately just think of the cables, the actual cords running through the ceiling plenums and plugging into server racks.
Which is fair. Cables are the primary physical manifestation, yes. But conceptually, the physical layer is the realm of raw signaling.
Just the actual ones and zeros.
Exactly. It's the transmission of binary data across a medium. Whether you're transmitting a 4K video conference, executing a massive database migration, or just sending a simple text string, that info ultimately has to be translated into a physical signal that can travel through space or matter.
And our sources categorize the media used for this signaling into three main types, right? Air, metal, and glass.
That's the triad.
So air being radio frequency for wireless and cellular, metal being copper cables like unshielded twisted pair, and glass being optical fiber. I kind of want to dive straight into the glass
Yeah.
because the mechanics of fiber optics are just fundamentally different from shooting electricity down a copper wire.
Oh, it's fascinating because it isn't just a hollow tube of glass.
Right, it's way more complex than that.
Far from it. Fiber optic cables actually utilize a highly engineered glass core, which is incredibly thin. I mean, sometimes as narrow as a human hair. And that core is surrounded by another layer of glass called the cladding.
So wait, why 2 layers of glass? What does the cladding actually do in that setup?
It comes down to the physics of light, specifically a principle called total internal reflection.
Okay, sounds very sci-fi.
It kind is. The core and the cladding are manufactured with different indices of refraction. So when a laser or an LED pulses light into the core, the light naturally tries to escape out the sides.
Or bleeding out into the cable.
Right. But because the cladding has a lower refractive index, the light hits the boundary between the core and the cladding and reflects entirely back into the core.
Oh, wow.
Yeah, it literally just bounces its way down the cable with almost zero signal loss. This allows the light pulses, which again represent our ones and zeros, to travel over massive distances without degrading.
Which is something copper simply cannot do.
Exactly, because electrical resistance naturally degrades voltage over distance. Light doesn't have that problem.
But the truly fascinating part of fiber architecture, and where the real business value comes in for managers, is a technology called Wavelength Division Multiplexing, WDM.
WDM is a game changer.
From a strategic standpoint, this seems like an absolute cheat code for IT infrastructure. Our sources indicate that WDM allows bidirectional, full duplex communication over a single strand of glass. Can you break down the mechanics of that?
Sure. To understand WDM, think about how a prism splits white light into a rainbow.
Okay, tracking?
Light travels in wavelengths, and different wavelengths basically correspond to different colors. Traditionally, a piece of fiber optic equipment might send a single wavelength of light down the cable. If you wanted to double your network capacity, you literally had to run a second physical fiber optic cable.
Which requires construction, right? Digging trenches across a corporate campus, pulling cable through concrete conduits. Massively expensive.
Unbelievably expensive and disruptive. Trenching new fiber is a huge capital expenditure. Wavelength division multiplexing changes that financial model entirely.
Oh, so?
Instead of laying new glass, you just upgrade the transceivers on the ends of the existing glass. WDM takes multiple data streams, assigns each one a specific, distinct wavelength or color of light, and multiplexes them simultaneously down the exact same fiber core.
And they don't crash into each other.
No. Because the wavelengths don't interfere with each other, they can pass right through one another.
So you could literally have one color of light carrying a database backup heading north, while another color of light carrying, like, VoIP traffic is heading south on the very same microscopic strand of glass at the exact same time.
That is full duplex communication in a nutshell. You multiply the capacity of your existing physical asset, your sunk cost exponentially, simply by upgrading the optical endpoints.
That is a massive return on investment for infrastructure managers.
Huge. It's one of the best upgrades you can make.
That actually brings up an interesting tension regarding layer 1 reliability. When we're evaluating the stability of these physical media, whether it's WDM over glass or just voltage over copper, how should an enterprise leader categorize reliability? Because just saying the network is down is a pretty broad complaint.
Yeah, that's a critical distinction to make. In enterprise infrastructure, layer 1 reliability is actually evaluated across two distinct metrics: availability and integrity.
Okay.
They are often conflated by users, but they require entirely different management strategies from an IT perspective.
Define availability first. What does that mean in this context?
Availability is just the physical presence and operational status of the link. Is the cable intact? Is the switch port receiving power? If a backhoe digs up the fiber line connecting your primary data center to your backup site, your availability is 0. The link is physically broken.
Got it. And integrity.
Integrity assumes the link is available, but it asks whether the data arriving at the destination perfectly matches the data that was actually sent.
Did the ones and zeros survive the journey?
Exactly. For example, if you run unshielded copper cabling too close to a massive industrial HVAC unit, or say an elevator motor, the electromagnetic interference, the EMI, can induce stray voltages on your copper wire.
So the link is technically up.
The link is up, the availability is there, but the electrical interference is flipping zeros to ones and ones to zeros. The data is corrupted, so the integrity is destroyed.
And as an IT leader, you have to design architecture that guarantees both. Which really leads us right into the physical deployment of these cables, the concept of structured wiring systems.
Yes, structured wiring is essential.
What differentiates a structured wiring system from just, running a really long cable from a server out to a desk?
A structured wiring system is a heavily standardized hierarchical architecture for enterprise cabling. It's modular, highly organized, and designed to support rapid moves, adds, and changes without having to constantly re-engineer the building's infrastructure.
It provides a blueprint.
Exactly, and it always starts at the main distribution frame, or the MDF.
The MDF is basically the primary data center, right?
Yeah.
Or the main telecommunications room where the external internet feed actually enters the building.
Correct. The MDF houses the core switches and routers. From the MDF, heavy-duty backbone cables, which are usually fiber optics, run vertically up through the building's risers to smaller wiring closets located on each floor.
And those are the IDFs, right?
Or the intermediate distribution frames, the IDFs. And finally, from those IDFs, horizontal cabling, typically your copper-twisted pair, runs through the ceiling and drops down into the wall, jacks at individual employee workstations.
I always look at this like constructing a massive commercial skyscraper.
It's a great analogy.
Right. You pour a massive concrete foundation and you build in massive plumbing and electrical conduits. You don't want to rip open the foundation or tear down load-bearing walls every 3 years just because a new department moves in, or you decide to upgrade the bathroom fixtures.
No, that would be a nightmare.
You want the foundation to be completely agnostic to what happens on the surface.
That analogy holds up perfectly when you're evaluating capital expenditures. A structured wiring system is a foundational generational investment. A well-designed cabling infrastructure has a typical operational lifespan of 10 to 25 years.
Wow. That is an eternity in enterprise technology. I mean, laptops are replaced every 3 years, servers maybe every 5, software is updated weekly, but the copper and glass in the walls stays for 2 decades.
Which means if management decides to, say, cut corners on the structured cabling during a new facility build-out just to save maybe 10% on the construction budget, they are artificially bottlenecking every single piece of advanced technology the company will purchase for the next 20 years.
You're capping your own potential.
The cabling dictates the absolute speed limit of the enterprise, period.
Okay, so we have the raw signaling. We have the glass, the copper, the MDFs, and the IDFs. We have established the physical road. But Chapter 4 covers both Layer 1 and Layer 2. Layer 2 being the data link layer.
Yes, moving up the stack.
I actually want to push back on the architecture here because to a business leader, this might seem a little redundant. If Layer 1 is already carrying the electrical voltage or the light pulses from point A to point B, why do we need an entirely separate layer of protocols just to format it?
Well, because without Layer 2, Layer 1 is just a chaotic, continuous stream of raw voltage. It means absolutely nothing.
Just noise.
Exactly. Imagine a highway where there are no cars, no lanes, and no license plates, just loose car parts rolling down the asphalt at 60 miles an hour.
That sounds like a mess.
It is a mess. The data link layer, Layer 2, is the vehicle. It takes the raw, unstructured bits from Layer 1 and organizes them into a structured, logical container called a frame.
Okay, so it's essentially placing a letter into an envelope and then writing a very specific delivery address on the outside of that envelope.
Precisely. And in networking, that specific delivery address at Layer 2 is the MAC address, the Media Access Control Address.
How does the MAC address function differently than, say, an IP address? Because we hear a lot about IP addresses in tech.
Sure. And we will cover logical IP addressing extensively in the next chapter. But the critical distinction here is permanence and physical location.
Permanence, meaning it doesn't change.
Right. An IP address is logical. It can change depending on what network you happen to connect to today. But a MAC address is a physical address burned into the actual silicon of the hardware.
Literally hard-coded.
Literally. Every single network interface controller, or NIC, manufactured in the world, whether it's the Ethernet port on a server or the Wi-Fi chip in your smartphone, has a globally unique MAC address permanently assigned to it by the manufacturer.
So the MAC address is the absolute unchangeable identity of the hardware device itself.
Exactly. So when a device wants to communicate, it encapsulates the data inside a Layer 2 frame. The header of that frame includes the source MAC address, identifying exactly which piece of hardware sent it, and the destination MAC address, identifying exactly which piece of hardware is supposed to receive it.
And without that envelope, what happens?
Without that layer 2 framing and addressing, a computer receiving a stream of voltage from a cable wouldn't know where the data started, where it ended, who sent it, or if it was even meant for them in the first place.
That makes perfect sense. Layer 1 is the physical highway. Layer 2 provides the vehicles and the permanent license plates. But if we have hundreds of these vehicles trying to merge onto the same corporate highway at the exact same time, we need traffic laws.
Desperately.
Which brings us to the most ubiquitous traffic system in the world, the IEEE 802.3 standard, widely known as Ethernet.
Ethernet is the undisputed workhorse of enterprise local area networks. And it's vital to understand that Ethernet didn't win the protocol wars by being, theoretically perfect. It won by solving immediate, painful business problems.
Let's trace that evolution, because the sources note that Ethernet was initially developed by Xerox back in the 1970s. What was the actual business driver there?
Well, early corporate computing consisted of these isolated islands. You had really expensive mainframes, a growing number of personal computers, and incredibly expensive peripherals like laser printers.
Right.
IT managers were facing a logistical nightmare trying to share resources. Passing floppy disks around was inefficient, and obviously buying a laser printer for every single employee was financially impossible.
So they needed a unified way to connect these isolated devices over a shared medium just to share files and hardware.
Yes. And the Institute of Electrical and Electronics Engineers, the IE, eventually standardized Xerox's work under the 802.3 specification. And if you map the evolution of the 802.3 standard over time, you're essentially mapping the enterprise's insatiable demand for bandwidth.
It's crazy how fast it evolved. The timeline in the sources starts around 1983 with a standard called 10^5.
Ah, yes. 10^5 was often referred to as Thicknet. It utilized a very thick, rigid coaxial cable. It provided 10 megabits per second, which, was revolutionary at the time.
But there were drawbacks, obviously.
Yeah, huge drawbacks. The cable was incredibly difficult to install, totally inflexible, and troubleshooting a break in it was a nightmare.
So the real breakthrough for standard office environments seems to be the shift to twisted pair cabling.
That was the massive turning point. The standard became 10^T. The T stands for twisted pair. Instead of rigid coaxial cable, networks began utilizing unshielded twisted pair copper wire.
Now, why is the wire actually twisted? Is that just for flexibility when running it through walls?
No, it's actually a brilliant feat of physics used to maintain data integrity. Remember we talked earlier about electromagnetic interference corrupting data?
Right, the EMI from elevators and HVACs.
Exactly. When an electrical signal travels down a copper wire, it creates a small electromagnetic field around it. If you run two wires parallel to each other, the field from one wire interferes with the signal on the other. This is called crosstalk.
So the signals bleed into each other.
Right. But by twisting the pairs of wires around each other at specific intervals, the electromagnetic fields generated by the wires effectively cancel each other out.
That's ingenious.
It is. It protects the integrity of the signal over longer distances without needing heavy, expensive shielding.
That is incredible engineering. So 10^T used this twisted pair to deliver 10 megabits. But the business demand didn't stop there, obviously.
Not at all. By 1999, the IEEE ratified 802.3AB, which is 1,000^T.
Gigabit speeds.
Yes. This was a monumental leap to gigabit Ethernet 1,000 megabits per second, running over the exact same style of inexpensive twisted pair copper cabling. It completely democratized high-speed networking.
And the standard continues to adapt to new business use cases even today, right?
Oh, absolutely. For example, a much newer standard, 802.3CG, provides a very modest 10 megabits per second, but it does so over a single pair of copper wires, and it can travel vast distances.
Wait, why would a manager want to go back to 10 megabits per second in the modern era when we have gigabit and beyond?
For the Internet of Things or industrial automation. If you have, say, thousands of temperature sensors spread across a massive manufacturing plant, those sensors do not need gigabit speeds just to transmit a tiny string of temperature data.
They just need a pulse.
Right. But they do need incredibly cheap, lightweight wiring that can run for thousands of feet without requiring expensive signal repeaters. 802.3CG solves that specific industrial problem perfectly.
Okay, so Ethernet evolved to utilize better physical media and deliver higher speeds. But we still haven't addressed the core mechanical problem, which ties right back to our opening hook.
The collisions.
Yes. If you have hundreds of computers in a corporate office all plugged into the same copper network, and they all decide to send their layer 2 frames at the exact same time, How did the electrical signals not just crash into each other constantly?
Well, in the early days of Ethernet, they absolutely did, and managing those crashes was the central genius of the original protocol. Early Ethernet utilized a mechanism with a rather formidable name, Carrier Sense Multiple Access with Collision Detection, or CSMED.
CSMACD. We definitely need to dissect how this actually operates at the silicon level, because it dictates the performance of the entire network. How does a network interface card actually sense the carrier?
It's basically a continuous process of listening. Imagine a network interface card that wants to transmit a frame of data. Before it sends a single bit, it listens to the physical copper wire.
What is it listening for?
It's sensing for a carrier signal, which in technical terms just means it's measuring the voltage level on the wire. If it detects a baseline voltage, it knows that another device on the network is currently transmitting. The wire is occupied.
So the rule is simply, if someone else is talking, you wait.
Exactly. The NIC will hold its data in a buffer and just wait until the voltage drops to zero, indicating the wire is clear.
I was trying to conceptualize this, and the most accurate business analogy I can think of is a highly efficient, but maybe somewhat chaotic, corporate boardroom.
Oh, let's explore that. That's a good way to frame it.
So you're sitting at a massive boardroom table with 50 other executives. You need to make a point. But before you open your mouth, you listen. If the chief financial officer is currently speaking, you don't interrupt. You wait.
You sense the carrier.
Exactly. You sense the CFO's voice. That's the carrier sense. And because anyone in the room has the right to speak when it's quiet, that is the multiple access. When the CFO finishes their sentence and the room goes dead silent, you immediately start speaking.
That perfectly illustrates the protocol. But in a room of 50 ambitious executives, what happens when the CFO stops speaking and both you and the chief marketing officer decide to start speaking at the exact same microsecond?
We talk over each other. It's a collision. In a boardroom, it's just awkward.
Yeah.
But on a network cable, what actually happens to the data?
On the physical wire, when two NICs transmit simultaneously, their electrical signals propagate down the copper and literally crash into each other. This causes the signals to combine, creating a sudden, measurable spike in the voltage amplitude on the wire.
A physical collision.
Yes, that is a physical collision.
And what happens to the data frames from both devices?
They're destroyed, completely corrupted. The voltage spike ruins the integrity of the ones and zeros.
Ouch.
But here is where the collision detection part of the protocol activates. The transmitting NICs are constantly monitoring the voltage of their own transmissions. The instant they detect that abnormal voltage spike, they know a collision just occurred.
How do they recover from it? Do they just try sending it again immediately?
No, because if they both tried again immediately, they would just collide again in an endless loop. The recovery process is highly structured. First, the detecting NICs immediately abort their data transmission.
Okay, they stop talking.
Right. Then they send out a special jam signal, which is usually a 32-bit frame of junk data, which propagates across the entire network. This jam signal ensures that every other device on the network is explicitly aware that a collision just happened and the network is currently unstable.
It's like someone blowing a whistle in the boardroom to stop the argument.
Precisely. Once the jam signal is sent, the devices involved in the collision execute a backoff algorithm. This is technically called truncated binary exponential backoff.
That is a mouthful. What does it actually mean?
It just means each NIC generates a random number which dictates a tiny microsecond delay before it is allowed to listen to the wire and try transmitting again.
Oh, I see. And because the delay time is random for each device, the probability of them colliding a second time is significantly reduced. One will wake up from its random delay slightly earlier than the other, sense that the wire is clear, and successfully transmit its frame.
That is the elegance of CSMACD. It is a completely decentralized, self-governing traffic control system, but it has a fatal flaw regarding scale.
I can definitely see that. I mean, in a small boardroom with 5 people, polite listening and occasional collisions are manageable. But what happens when you put 500 people in that boardroom? Or 1,000?
The protocol just collapses under its own weight. As you add more devices to a shared Ethernet network, the sheer mathematical probability of 2 devices trying to speak during the same microsecond skyrockets.
So the network just becomes utterly saturated with collisions, voltage spikes, jam signals, and devices stuck in random back-off timers.
Exactly. The actual productive throughput of the network falls off a cliff. A network that can theoretically push 100 megabits per second might only deliver, say, 20 megabits of actual data because 80% of the bandwidth is consumed by collisions and retransmissions.
And this directly explains why early network hardware designs were so problematic. I know our sources discuss the transition from hubs to switches, which is really foundational for any IT manager to grasp, because in the early days, businesses were using hubs to connect these networks, right?
Yes, a hub is the device that essentially created that massive, noisy boardroom. Physically, a hub looks like a simple box with multiple Ethernet ports, but internally a hub is a very unintelligent Layer 1 device. It is essentially just a multi-port repeater.
Meaning it doesn't process data at all, it just pushes electricity.
Exactly. When an electrical signal carrying a frame enters port number 1 on a hub, the hub does not read the MIC address. It doesn't look at the layer 2 envelope at all. It simply takes that raw electrical voltage, amplifies it, and blindly blasts it out of every single other port on the device.
So if my computer tries to send a print job to the network printer, the hub sends that print job to the printer, sure, but it also blasts it to the receptionist's computer, the server, the CEO's laptop. Literally every single device on the hub receives the signal.
Everyone hears everything. This creates what network engineers call a single massive collision domain.
Let's define that term clearly, a collision domain.
A collision domain is a specific segment of a network where data packets can collide with one another when sent on a shared medium. If you have 50 computers plugged into a series of interconnected hubs, all 50 computers are in the exact same collision domain.
So they are all sharing the exact same pool of bandwidth, and they can all interrupt each other at any moment.
Yes, which is incredibly inefficient from a performance standpoint, but it's also a massive security risk.
Oh, because everyone gets the data. If a hub blindly broadcasts every piece of data to every port, any compromised device on that network can just run a packet sniffer and read everyone else's traffic.
It was a huge security vulnerability. Any user could capture unencrypted passwords or sensitive files just by listening to the wire. Hubs were really just a temporary hardware solution that didn't scale. The enterprise needed a way to tame the traffic. And that brings us to the most important hardware evolution in local networking, the Layer 2 switch.
The switch changes the paradigm entirely, doesn't it? From the outside, it looks identical to a hub, just a box with ports. But internally, the architecture is completely different.
Night and day, because a switch actually operates at Layer 2. It has internal processing power, specifically application-specific integrated circuits, or ASICs, designed to read data at wire speed.
Wow.
Yeah. So when a frame enters a switch port, the switch doesn't just blindly repeat the voltage, it actually reads the Layer 2 envelope.
It looks at the MSE addresses.
Yes. The switch looks at the destination MSE address of the incoming frame. It then checks an internal database called a MSE address table, or a CAM table. The switch says, okay, I see this frame is destined for MSE address XYZ. My internal table tells me that the device with MSE address XYZ is physically plugged into port 12.
So instead of blasting the signal out of all 24 ports, it seamlessly switches the electrical connection and sends the data only out of port 12.
Precisely. It creates a temporary, dedicated microcircuit between the sender and the receiver.
How does that solve the collision domain problem?
This is a core managerial takeaway here. A Layer 2 switch completely breaks up collision domains. Because the switch buffers the frames and only sends them to the specific destination port, collisions between different devices are eliminated. Completely. In fact, on a modern switch, every single port is its own isolated collision domain.
So going back to our boardroom analogy, the switch acts like an advanced telecommunications operator. It takes a chaotic room of 500 shouting executives and instantly places each one of them into a private, soundproof telephone booth, connecting them directly only to the person they actually need to speak with.
That is exactly what it does. Full duplex switching allows every device to transmit and receive simultaneously without ever crashing into another device's data. It reclaims all of the bandwidth that was previously lost to collisions.
Okay, I have a major pushback here.
All right, let's hear it.
Because if a switch is this intelligent, if it isolates traffic and only sends data to the intended recipient, then how do we explain the catastrophic trading floor crash from our opening scenario? If switches stop collisions, are we totally immune to broadcast storms?
That is the critical question, and the answer is absolutely not. We are not immune.
But why?
Because while switches eliminate collision domains, they do not eliminate broadcast domains.
Okay, break down the distinction between those two domains.
We established that a switch stops collisions by forwarding traffic only to the specific destination MAC address, right? But there are times when a device needs to communicate with every other device on the network simultaneously.
Give me a real-world enterprise example of when that actually happens.
The most common example is IP address resolution. Say a new laptop connects to the network. It doesn't know where the central server is. So the laptop sends out a special layer 2 frame called a broadcast frame.
And what makes it a broadcast frame?
The destination MAC address on this frame is essentially formatted as all Fs, which is a universal address that means everyone.
And what does a layer 2 switch do when it receives a broadcast frame?
By rule, when a switch receives a broadcast frame, it must replicate that frame and flood it out of every single active port except the one it received it on. It essentially has to act like a hub for that specific frame.
So every device on the switch receives the broadcast.
Correct. And if you have, say, 50 switches interconnected across a massive hospital campus, the broadcast frame is forwarded across the trunk lines to every other switch, and those switches flood it out to every one of their ports.
Oh, man.
Right. Every single device across the entire physical network receives the broadcast and must process it.
So that entire interconnected architecture is considered a single broadcast domain.
Yes, a broadcast domain is the entire logical boundary of devices that will receive a broadcast frame.
So returning to the catastrophic crash, how does this turn into a storm?
Well, in a properly functioning network, occasional broadcast frames are just normal background chatter. But networks are physical systems. They fail. Let's say a network technician accidentally plugs a cable into 2 ports on the exact same switch, or connects 2 switches together in a circle, creating a physical loop.
A loop? What happens to a broadcast frame when it hits a looped architecture?
It creates an infinite amplification cycle. Switch A floods the broadcast to switch B. Switch B floods it back to switch A. Because there is no mechanism at layer 2 to destroy old frames, the switches just continuously pass the broadcasts back and forth at wire speed.
Just bouncing back and forth forever.
Forever. Furthermore, if a faulty network card on a server malfunctions and starts rapidly generating thousands of broadcast frames a second, the switches will faithfully replicate every single one of them to every port on the network.
The volume of traffic just expands exponentially.
Within milliseconds,
Yeah.
the network links become 100% saturated with redundant broadcast traffic. The CPUs on the switches completely max out trying to process the frames. Valid data like a patient's vital signs or a massive financial trade cannot get onto the wire because there is absolutely no bandwidth left.
Everything is choked out.
The entire enterprise infrastructure just locks up. That is a broadcast storm.
It is terrifying because the switches are just blindly following their programming, right?
Yeah.
They're doing exactly what they were designed to do, but it results in a total systemic failure.
Which is why IT managers cannot simply buy 1,000 switches, plug them all together, and expect the network to function. You have to actively design boundaries to contain those failures. You have to build a topology.
Which perfectly transitions us into network design fundamentals, the sort of city planning aspect of telecommunications. If the switches are managing the intersections, how do managers actually design the overall map of the digital city to prevent these cascading failures?
Network architects typically segment corporate infrastructure into a hierarchical model consisting of 3 core levels: access networks, distribution networks, and core backbone networks.
Let's start at the edge, the access networks.
The access network, commonly referred to as the edge, is the exact point where end-user devices connect to the corporate infrastructure. This is the last 100 meters of copper wire running from the IDF wiring closet down the hallway to the desktop computers, the VoIP phones, the printers, and the wireless access points mounted on the ceiling.
When planning this edge network, one of the most strategic hardware capabilities a manager can deploy is Power over Ethernet, right, or PoE. From a pure operational expenditure standpoint, PoE fundamentally changes how IT scales physical deployments.
It's one of the highest ROI technologies at the access layer, without a doubt. PoE switches are designed to inject standard electrical DC power alongside the data signals over the exact same copper twisted pair cable.
Meaning I don't need to hire an electrician to install a high-voltage wall outlet next to every single device I want to deploy.
Exactly. Consider a project where management wants to deploy, say, 200 new security cameras across a corporate parking garage and 50 new wireless access points in the warehouse. Traditionally, you would need licensed electrical contractors to pull heavy conduit, install junction boxes, and pull permits for every single location.
Which takes months and costs a fortune.
But with PoE, Your IT staff simply pulls a standard low-voltage Category 6 Ethernet cable from the PoE switch in the telecommunications closet directly to the camera.
And it just powers up.
Yeah, the switch negotiates the power requirements with the device and instantly delivers the wattage needed to power the camera while simultaneously providing a gigabit data connection.
That drastically accelerates deployment times. You can put a device literally anywhere you can run a low-voltage cable.
It provides immense agility, and the standards have evolved so much. Early PoE could deliver about 15 watts, which was enough for a basic VoIP phone. Modern PoE standards can deliver up to 90 watts over a single cable, which is enough to power high-definition, pan-tilt zoom cameras, point-of-sale kiosks, and even LED lighting systems for smart buildings.
Okay, so the edge network is powered and connected. Moving up a hierarchy, we aggregate these edge connections into workgroup and departmental LANs. What determines how a manager structures this middle layer?
The topology of a departmental LAN should be dictated purely by traffic analysis, specifically the volume and direction of data flowing between user groups.
Give me an example of how traffic patterns influence those hardware choices.
Sure, suppose you oversee an architecture firm. You have a massive team of CAD engineers who constantly pull multi-gigabyte 3D rendering files from a local storage server. That traffic is incredibly dense, but it stays entirely within their department.
Right.
You would design their workgroup LAN with ultra-high port density switches, like a massive 96-quart chassis, so that all the engineers and their server connect directly to the same high-speed switching backplane.
Why one massive switch instead of just, 5 smaller switches connected together?
Because every time data has to jump from one switch to another over an uplink cable, you create a potential bottleneck. High port density on a single switch provides the lowest cost per port and guarantees non-blocking wire speed performance between those specific users.
Got it. Keep heavy local traffic on local hardware. But eventually, those CAD engineers need to send those files to the marketing department across the building or out to the internet. We need highways connecting these departmental neighborhoods. We need backbones.
Backbones are the distribution and core layers of the network. They aggregate the traffic from all the local access switches and route it across the enterprise. The sources outline a few critical variations of backbone architecture, starting with the collapsed backbone.
The collapsed backbone. The name implies everything is centralized. How is it structured?
It's the dominant design for a single, large, multi-story building. You take the edge switches located in the IDF closets on every floor, and you run high-speed uplink cables from each of those switches directly down to one massive, highly redundant central switch located in the main data center on the ground floor.
So the entire routing core of the network is collapsed into this single hardware chassis.
Exactly.
That seems very clean to manage. But is there a physical drawback?
The primary challenge is distance limitations. Standard copper Ethernet can only reliably push gigabit speeds for 100 meters, which is roughly 330 feet. If you are aggregating a 20-story skyscraper back down to the basement, the cable runs from the top floors will easily exceed 100 meters.
Oh, of course.
Therefore, a collapsed backbone almost always requires pulling fiber optic cabling vertically through the building's risers to connect the floors.
Which obviously increases the initial capital expenditure, but provides future-proof bandwidth.
Exactly. Now, the alternative to this hierarchical routing design is a flat backbone.
What is a flat backbone, and why would an enterprise use it?
A flat backbone relies purely on layer 2 switching across the entire building without introducing routers to segment the traffic at layer 3. You're basically just daisy-chaining the switches together. It is cheaper and easier to set up for a small business.
But doesn't that bring us right back to the broadcast storm problem?
It absolutely does. A flat backbone means the entire building is one massive broadcast domain. If a broadcast storm initiates on the 10th floor, it instantly cascades across the flat backbone and takes down the entire building. A collapsed backbone, however, typically uses routers or layer 3 switches at the core to define boundaries. Routers do not forward broadcast frames. They act as firewalls for broadcast traffic, containing any storms to the specific floor where they started.
That is a critical structural insight. The router at the center of the collapsed backbone acts like a bulkhead on a submarine. If one compartment floods, you seal the door, and the rest of the ship survives.
That is a very accurate way to visualize it, yeah.
Okay, so that covers a single building. What if the enterprise footprint is much larger? What if we're managing a state university or a corporate headquarters comprised of 5 separate buildings spread across 100 acres?
Then you scale up to a campus backbone. The design logic is similar to a collapsed backbone, but the geographic scale is vastly larger. You are aggregating the core switches from multiple buildings into one central master data center.
And because of the distances between buildings, copper is entirely out of the question here.
Yes. A campus backbone relies exclusively on heavy-duty, multi-strand fiber optic cables laid in physical trenches beneath the ground or strung across utility poles.
And pushing the geography even further, enterprises rely on metropolitan area networks, MANs, and wide area networks, WANs.
Correct. If your enterprise needs to connect a manufacturing facility in the suburbs to a corporate office downtown, you would utilize Metro Ethernet provided by a commercial telecommunications carrier. If you need to connect an office in New York to a data center in London, you move into WAN technologies, often utilizing MPLS or SD-WAN overlays.
The fascinating aspect of this scalability is that the core Layer 2 envelope we discussed earlier, the IAKey 802.3 Ethernet frame, often remains exactly the same, whether it is traveling 10 feet across a room to a printer or traversing a fiber optic submarine cable across the Atlantic Ocean.
The protocol is remarkably resilient. It just scales.
But as we scale out to these campus and WAN architectures, the sheer volume of data being aggregated from thousands of endpoints is staggering. Which brings us to the final dimension of Layer 1 and 2 architecture, the need for speed.
Always need more speed.
Because as modern applications demand real-time 4K video conferencing, continuous off-site virtual machine backups, and massive database synchronization, these backbone highways have to support astronomical throughput.
The demand is relentless. We discussed the evolution to gigabit Ethernet, which is now the baseline standard for edge connectivity. But for the backbones, the links connecting the buildings and the server farms gigabit is nowhere near sufficient. The enterprise standard has rapidly shifted to 10 GigE, 10 gigabits per second.
Pushing 10 gigabits per second over a local area network protocol is impressive. But there is a specific technical metric from the sources regarding 10 GigE that blew my mind from a disaster recovery perspective. It involves the use of single-mode fiber.
You're referring to the distance specifications. Yes. 10 GigE deployed over single-mode fiber optics can support maximum transmission distances of 10 to 40 kilometers without requiring a single signal repeater.
40 kilometers. That is roughly 25 miles. The strategic implications of that for an IT manager are massive.
They are profound. Consider a bank that requires instantaneous data replication for financial compliance. With 10 GigE over single-mode fiber, a manager can establish a primary data center downtown and a fully redundant disaster recovery facility in a different city 20 miles away.
And there's no lag.
Because the connection is operating at 10 gigabits at Layer 2, the servers in the remote facility act exactly as if they are sitting in the rack next door. The latency is practically non-existent.
What makes single-mode fiber capable of pushing that much data over 25 miles, as opposed to the fiber used inside a building?
It comes down to the width of the glass core and the light source. Multi-mode fiber, which is common inside buildings, uses a wider core and inexpensive LEDs. The light bounces around a lot as it travels, which eventually causes the signal to blur over long distances, a phenomenon called modal dispersion.
Okay, and single-mode.
Single-mode fiber uses an incredibly narrow core, measuring only a few microns across, and utilizes highly calibrated lasers. The laser pulse travels straight down the exact center of the core without bouncing off the cladding. The signal maintains perfect integrity for tens of kilometers.
So it's like a sniper rifle versus a shotgun.
Precisely. But even with 10 gigabit connections, enterprise architecture faces bottleneck challenges, particularly at the core data center.
Let's look at that scenario. You have a massive centralized server farm. Hundreds of servers are processing data, and they all need to push that traffic out to the campus backbone simultaneously. If you connect that core switch to the campus with a single 10 gigabit fiber line, that line immediately becomes a massive choke point.
It does. And you cannot simply invent a 50 gigabit standard overnight when the hardware only supports 10. So how do network engineers solve this physical limitation? They aggregate the connections. This technique is called backbone trunking or link aggregation.
So we literally just physically bundle multiple cables together.
Physically, yes, you run multiple fiber cables between the switches, but logically, it is managed by a protocol, often LACP, or Link Aggregation Control Protocol. The switches are configured to treat 4 separate 10 gigabit fiber links as one single massive 40 gigabit logical pipe.
So it takes our 10-lane highway and seamlessly turns it into a 40-lane highway. But how does the switch decide which data goes down which physical cable?
The ASIC inside the switch uses a mathematical hashing algorithm. It looks at the source and destination MAC addresses, or IP addresses, of the data flow, runs a calculation, and assigns that specific conversation to one of the physical cables in the bundle.
And the major business benefit here isn't just raw speed, is it? It's resilience.
Absolutely. Trunking provides active immediate fault tolerance. If you have 4 fiber cables bundled together and a contractor accidentally cuts one of the physical lines, the entire link does not go down. The switch's layer 1 sensors instantly detect the loss of voltage or light on that specific port.
And then what?
Within milliseconds, the switch recalculates the hash and seamlessly redistributes all the traffic across the remaining 3 cables.
The total capacity of the trunk drops from 40 gigabits to 30 gigabits, but the connection stays alive.
The enterprise doesn't crash, the VoIP calls don't drop, the database sync continues. From a managerial perspective, you have engineered a core architecture with no single point of physical failure.
Which really brings this entire architectural journey full circle. We started this deep dive exploring a catastrophic scenario, a hospital or a trading floor paralyzed by a broadcast storm, brought to its knees by the physical limitations of its own infrastructure.
And through analyzing these layers, the strategic solution becomes clear. A well-designed physical and data link layer is not merely IT overhead or a line item in a construction budget.
Far from it.
By leveraging generational structured wiring, deploying intelligent layer 2, switching to break-up collision domains, utilizing PoE to rapidly empower edge devices, and engineering high-speed aggregated fiber trunks, IT leadership transforms the network from a vulnerable cost center into a highly resilient, high-speed business enabler.
You cannot solve a layer 1 or layer 2 physical bottleneck by simply purchasing expensive cloud software. You have to get the foundation right. By properly designing the broadcast domains and upgrading legacy flat topologies to hierarchical architectures, managers actively engineer those catastrophic failures out of existence.
The foundation dictates the limits of the enterprise. But as we continually push those limits, I do want to leave our listeners with a strategic reality to consider.
Let's hear it.
For the last 4 decades, network engineering has mastered the art of sending pulses of light through glass and electrical voltages over copper to achieve astonishing speeds. But as enterprises aggressively deploy generative artificial intelligence, as IoT sensors proliferate into the millions, and as we generate exponentially more data every single operating hour, what happens when we finally collide with the immutable laws of physics regarding how much data a single physical medium can carry? How will your infrastructure adapt when we simply cannot pulse the light any faster?
Wow. That is a staggering strategic horizon to consider. But before we attempt to break the laws of physics, we have to finish constructing the map. Because today, we secured the physical roads and we structured the local vehicles. But how do those vehicles navigate a global interconnected map? How does a single packet of data know the most efficient path from a laptop in a Tokyo coffee shop to a secure server buried in a Chicago data center?
That's the next big piece of the puzzle.
Exactly. So stay tuned for Chapter 5, the network and transport layers. In our next session, we will shift focus from the physical wires to explore how logical IP addressing spans massive global topologies and how transport protocols brilliantly manage end-to-end data flow control across the planet.
I am highly anticipating that analysis. And as a reminder to our executive audience, if you found this architectural breakdown valuable, please take a moment to like, subscribe, and share this session with your IT leadership team.
And do not forget to access the description below for direct links to the structured wiring diagrams and the technical specifications we referenced today. While you are exploring those resources, we strongly encourage you to review the channel for our other corporate IT playlists. Specifically, check out our digital forensics and network and system security deep dive series to continue your professional education and broaden your strategic oversight.
As you evaluate your own organizational architecture this week, ask yourself, are your physical layers acting as a springboard for your digital strategy, or are they a hidden bottleneck restricting your growth? Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.